In this class we will see the different components involved in electrochemical cell and what are the different barriers to the electrochemical reaction which occurs in the electrolysis process. What are the different components, their requirements and how do they impact. So, if we look at the different components, then there is an electrode, electrolyte and diaphragm, and they need to satisfy certain requirements in the electrolytic cell. If we look at the barriers to the reaction which occurs in the electrolytic cell, that all depends upon the different components of the cell. Now these barriers could be, there could be boundary layers being formed at the electrode surface, then the electrode phase, its characteristics, the characteristics of the electrolyte involved, what kind of separator is being used, what are the different electrical resistances involved in the process, and all these determine the behavior of current, IV, efficiency and the amount of hydrogen being produced from a particular electrolytic cell. Let us look at one by one each of these. Now when we look at the electrode and an electrolyte interface, so this is the interface. At this interface there are differences occurring due to the surfaces. One is a solid surface, the another may be a liquid or a solid surface. There are differences in terms of the electrolyte velocity, there are difference because of the concentration of the active electroactive species, and there are differences which are arising because of the electric potential from the surface of electrode to a certain distance from the electrode. Now each of these differences, they give rise to a boundary layer at the interface. For example, let us consider the difference in the electric potential at this interface. Now if we try to plot, this is a model wherein we can see that if this is a negative electrode, on the surface of it there are positive ions, they form a sort of compact layer. Let us say if at the surface the potential is phi e, the electrode surface, this is a compact layer which is being formed, and the remaining there is a diffuse layer. So which has ions distributed more than that in the electrolyte close to the electrode. So because of that there is a variation in the potential. So at the surface if it is phi e, and at the electrode surface in the solution if it is phi s. So in this compact layer it varies linearly, and thereafter it varies in the diffuse layer, it varies exponentially. Because of the presence of this boundary layer, it acts as if there are two capacitances operating, one which is because of the compact layer and because of the diffuse layer. And similar to this boundary layer which is occurring because of the electric potential changes at the interface of electrode and electrolyte. Similarly, there are changes which are because of the electrolyte velocity, concentration, boundary layer, because of the change in the concentration of electroactive species, or it could be because of the change in the velocity of electrolyte in the vicinity of the electrode surface, and that could give rise to a hydrodynamic boundary layer. Now this concentration boundary layer, here it is the driving force is the diffusion, while in case of electrolyte velocity the charge separation is the charge separation is the driving force for the difference in the electric potential that occurs at the interface. However, when it is electrolyte velocity different giving rise to hydrodynamic boundary layer, the difference or the driving force is the convection in the process. Now when this difference in the potential phi E minus phi S is existing, that double layer at interface has several consequences. Now this potential difference which is arising phi E minus phi S, that provides the required driving force for the electron to transfer between the electrodes across the electrodes, and that driving force however gets affected because of the adsorption of different species at the electrode surface. Now these could be the reactants, these could be products, these could be the different ions, these could be contaminants involved in the process. Like in the earlier figure we have shown that these are the solvent molecules which get adsorbed onto the electrode surface, and that changes this potential difference in the process. There could be variations, localized variations which occur because of the potential difference, and that in fact influences the rate of the reaction, the efficiency of the process as well as the selectivity towards hydrogen being produced. At the same time, this potential difference which is arising across the interface, that can be very high. Like for example, if phi E minus phi S is equal to 2 volt over 0.2 nanometer, the potential gradient will be 10 raised to power 10 volt per meter. Such a high and localized driving force enables energetically difficult processes to be carried out electrochemically. The double layer capacitance measurement can provide information on adsorption at electrodes, however it tends to create problem in kinetic studies, particularly where high surface area electrodes are involved and when there is rapid potential changes with time due to charging currents. Now let us look at the electrode phase. Now the electrode phase, the requirement for electrode phase is that it should be mechanically stable. Mechanically stable, it should not undergo erosion. When it is acted upon by different reactants, by different products, in the presence of different ions. So there should not be any loss of electrode when it is subjected to different species. At the same time it should remain physically and chemically intact. This electrode which is being used, it should be easily integrable. By easily integrable we means in an electrolytic cell this can be easily connected, giving rise to good electrical connections, and when required can be taken out for inspection or for maintenance. The shape and surface of the electrode phase, that also is very important in the sense that this is the place where the various electrochemical reaction occurs. Surface should be such that it should allow the reactants to get reacted and the products formed to be removed in the process. Now what happens in these electrodes is usually a very thin coating of is considered on a bulk material. The electrodes should be such that the desired reactions should be achieved. Desired reactions which leads to the formation of the gaseous product. However, certain unwanted chemical reactions can be avoided, and these desired reactions should occur with a high rate of reaction, and as such that will define the efficiency of the process, the current density involved in the process. The electrode should have good electrical conductivity, and it should definitely have a low cost and high life. Now, when we look at the processes involved on the electrode surface, then there are two types of electrode processes. One is where it acts as electron source or sink, and reaction kinetics are sort of independent of electrode material. Second, electrode surface acts as catalyst, and the type as well as rate of reaction depends on interactions between the electrode and electrolyte species. Thus, a rough surface can provide a high and active electrode area to increase the electrocatalytic effect. In water electrolyzers, an electrocatalytic electrode surface is required to promote a hydrogen and oxygen evolution at high rate and at low over voltage. Similarly, if we consider the electrolyte phase, then there are three components of it: a solvent which is required, which should remain stable under the reaction conditions, an electrolyte and the electroactive species, and these electroactive species are nothing but the reactants. So, now when we look at the electrolyte, the solvent should be such that it should be cost effective, it should be stable, it should be easy to handle, that means its disposal as well as handling should be safe, and recycling of that should be safe. So, as such, if we look at these solvent, then water is the most promising solvent, and the reason for water being used as a solvent is that it is not only the low cost, stable, the same requirements, it forms an oligomer. So, it has a high dipole moment, and this high dipole moment allows the interaction of the electroactive species. At the same time, the splitting up of or the ionization of water, it is very small into H plus or OH minus. So, it remains stable under the operating conditions. So, as such, it is an ideal solvent. So, self ionization of water is relatively very small. If we look at the electrolytes, then the high conductivity in the solution phase is the requirement, and that electrolyte that has to disintegrate or dissociate to form anions and cations. What is required is that it should have a high conductivity in the solution phase, and this high conductivity will lead to definitely the low resistance, it will result in anions and cations which will basically carry the current. Of current, and it will have a high ionic strength. and that results into equal and constant activity. Coefficient for the reactants and products. So, if we look at the electrolytic conductivity, this is represented by either the molar electrolytic conductivity times the electrolyte concentration. Molar electrolytic conductivity times the concentration, and it can also be written as conductance times the cell constant. And usually for typical cases, this electrolytic conductivity, it lies in the range of 5 to 25 Siemens per meter, and this is when the typical concentration is of the order of say 1 mole per decimeter cube. So, this is usually the electrolytic conductivity being observed. Another important component of an electrolytic cell is a separator. Now, separator, although if it is present, it has several advantages, but the presence of separator also leads to disadvantages, that like it will add on to the cost, it will add on to the complexity of the system, and also it will increase the resistance to the flow of ions. However, separator also plays certain important role, like in the presence of separator, the two electrodes, they are physically separated, and that prevents sorting. The gaseous products which are released formed in the electrochemical reactions, they are separately produced. So, their intermixing is prevented. At the same time, we can use independent cathode, catholyte and anode, anolyte in the presence of a separator. It can also prevent the redox shuttle, which is in fact parasitic in nature. So, parasitic redox shuttle, which is when the species can undergo reduction at one electrode and it can undergo reoxidation at the another electrode, and that can be avoided. At the same time, the separator can be selective towards one ion, and it can selectively allow that particular ion in transport of ions. There are different types of separators which are available. These can be either porous separators, or these are also called spacers. Now, these porous separators, they are such that they can sort of provide support to in fact fragile electrodes. They can even provide support to membranes being used, and they can promote a sort of turbulence at the electrode surface. However, they cannot prevent the movement of solvent, they cannot stop the mixing up of anolyte and cathodite. They cannot prevent mixing of anolyte and cathodite. Now usually the pore size which is of these separators that lie in the range of 0.5 to 12 mm. Another category of separators which can be used are microporous, wherein the pore size is in micron dimensions. Microporous separators or diaphragms. And for them the pore size lies in the range of 0.1 to 50 micron, and they allow the transport of solvent, solute and ions through it by means of hydraulic permeability. However, there are barriers which are, because of the presence of these type of separators, the convection and diffusion type of barriers exist when these type of separators are being used. Or there can be another separator which are ion exchange type, which selectively allow a particular type of ions to flow through them. These are ion exchange membrane type of separators which can be used, and these in fact they divide the electrochemical cell into two compartments, and in that case we can use separate anode anolyte or separate catholyte we can use. However, they permit only the passage of ions, allows selective passage of ions. In the process they have a pore size which is small, 10 to the power minus 8 to 10 to the power minus 9 meters, and they also function in such a way that they are barrier to convection and diffusion. But there are several requirements when it comes to membranes being used in an electrolyzer. These membranes should have very high selectivity, and they should be able to permeate only a particular type of ions and not the neutral molecules. They should have high chemical stability under the reaction conditions when it is subjected to different reactants, products and different ions. These should be mechanically stable. So, they should be stable, at the same time they should provide strength and flexibility. They should have high ionic conductivity. But a lower electronic conductivity. They should be such that they should operate under variable current densities, can be able to operate at high current density, when it is operating under full operation, or it should be also be able to operate under lower current densities, and at the same time they should be homogeneous in structure, so that there should not be local variations. It should have throughout the same uniform current densities. It should be easily available, convenient to handle and economical. So, low cost and high life of these membranes. which can be used in a electrolyzer. To summarize this portion, we have seen the different components involved in the electrolytic cell, what are the different requirements for electrode, electrolyte and separator, and how these components, what kind of roles they play in an electrolyzer. So, in the next class we will see the kinetics involved in the process and how to find out the efficiency of an electrolyzer. Thank you.